recording. Here we go. I'll add a page because hey, can't see me struggling, but there I am. All right. We're going to continue probability. In fact, we were working on conditional probability. Conditional probability in general looks like this, right? The probability of A given B. Remember, you read this as given that vertical line. So A given B. It's on your formula sheet, right? But as we get more used to working with the conditional probability, right, it's going to be the probability of A and B divided by the probability of B, the second term. And so it's going to be the probability of A and B divided by the probability of B. And the A's and the B's are just placeholders, right? And so you can replace them with any variable that you'd like, right? And one way to solve conditional probability questions is we often use tree diagrams to solve conditional probability questions. Tree diagram in general, right, is just to help us visualize possible outcomes, attach probabilities to them. And so one of the examples that we saw last day was the cancer question, right? Where someone either has cancer or they don't, right? Those are the first two possible outcomes. And we said, okay, usually I write the probabilities below each of these. I don't tend to use probability notation, right? Because it's just to help me visualize the problem and map out what I'm trying to find. But then you can either have a positive test or a negative test, or if you prefer positive and not positive. But in this case, I think it's more clear if you do positive and negative test, right? And so here, the probability of getting a positive test given that this person does have cancer was different, right, from the probability of a positive test knowing that they didn't have cancer, right? And so we were given all those probabilities. I don't want to redo the entire question, but what we were saying was that the probability of a positive given cancer is the probability that I put in on this branch, right? 1 minus that is going to be the probability of a negative test, right? Given that they're down the cancer branch. So this is the probability of a negative given that they have cancer. Same thing, a positive test knowing that they don't have cancer, so knowing that they're down this not cancer branch is the probability of a positive test given not cancer. And again, 1 minus that is the probability of negative given that they do not have cancer. So at the bottom of each of these, I like to summarize what the combinations are, right? cancer and a positive test, cancer and a negative test, not cancer and a positive test, and not cancer and a negative test. Saying and, so the probabilities here, I'm going to multiply down the branch, right, to find each of these and probabilities. We multiply down the branch to find the probabilities, or the probability of each combination. This is a list of all possible outcomes. And from the sample space, we remember, okay, the sum of those probabilities has to be 1. The sum of the probabilities for all the branches we must be 1. So now, right, we can use this tree to find all different kinds of probabilities. And often I'll make you find a probability of one of these end results. So the probability of a positive test is what we did, right? And so we said, okay, well, there's actually 2 ways that I could have a positive test. They could have cancer and have a positive test, or, right? And when we say or, we're adding, or they could not have cancer and have a positive test, right? And so we said there's 2 ways that I could get a positive test. And so to find the overall probability of a positive, the probability of a positive test is going to be the probability of cancer and a positive test plus the probability of not cancer and a positive test. Because when you read these and you say or, you're going to add them, right? Okay. So then we found, what was it we found? We found the probability of them having cancer given that they had a positive test. Going back to just the general form of the probability of A given B, I do the probability of the first and the second, right, in my numerator, and then I divide by the probability of the second thing, right, the overall probability of the second thing. So then this became the probability of the first and the second, which we've just been denoting as C plus, C and plus, divided by the probability of a positive, right? The probability of the second. Without numbers, might not jog your memory, but how about we do this, I'll call it the end of our review. So I wrote a note, start here on Thursday. And here we are on Thursday, I think. Oh, I keep forgetting. What do I keep forgetting? I put it on Moodle, but it might be nice for me to actually say it if I haven't already. I really can't remember. Test number 1 is on October 10th. Oops, almost wrote 11. Go to our Moodle page. This isn't us. This is us. Not so gross. So here, October 10th, we've got test 1, which is going to be on chapters 1 through 4. Kind of depends on how far we get. I just tend to cut it. Notice that I put I'll give you an outline for test 1, what to expect. I'll give you a practice test, right? And so next week, we're gonna start chapter 4. Whenever it says brief, I'll do like just a little sentence about it. So nothing crazy. We are doing it, quote unquote, but we're gonna focus on the normal distribution and the binomial distribution next week. So those will for sure be on test 1. And then I'm hoping to maybe get to the Poisson before the test. But in that case, because it's on the Tuesday and the test is on the Thursday, I usually do it as a bonus question, right? And so if it's kind of typed to the test like that. Okay, good. There, I said it. Whew. Almost forgot again. Did you read the application activity? I'll read it to you. So, a common epidemiological model for the spread of diseases is the SIR model, where the population is partitioned into 3 groups, being susceptible, infected, and recovered, SIR. This is, of course, a reasonable model for diseases like chickenpox, where a single infection usually provides immunity to subsequent infections. So knowing that someone has recovered, right, that tells us about the probability of them getting it again, right? Imagine a population in the midst of an epidemic where 60% of the population is considered susceptible, 10% is infected, and 30% is recovered. The only test for the disease is accurate 95% of the time for susceptible individuals. Okay? 99% for infected individuals, but 65% for recovered individuals. Okay? Now, this is looking like a tree diagram type of question, and it is, right? And so we're going to draw the tree, and I think, yeah, let's do it together instead. So let's start mapping things out. I haven't read the entire question yet, but I do want to highlight a couple of things for our tree. So first, our population is split into 3 groups, right? And so now I'm going to start with 1, 2, 3 branches. Right? Let's call it SIR, because it's the SIR model. Susceptible, infected, recovered. Maybe I'll try to make this a little bit bigger. Pretty good. Why is that the first branch or the first set of branches? Because all of these tests, right, we have probabilities for the accuracy, right, is accurate 95% of the time for susceptible individuals. So given that they are susceptible, then it's accurate 95% of the time. Given that they are infected, then it's accurate 99% of the time, right? And so we're we have to know if they're susceptible, infected, or recovered in order to determine where these probabilities are going to go. This one is a real doozy because accurate, right, means returning a negative result for susceptible and recovered individuals, right? Because to be accurate, then it should test negative, right? You don't have it yet, right? For susceptible and recovered, oh yeah, because you don't have it, because you haven't had it or you recovered from it, right? And then a positive result is accurate if you do have this, whatever it is. Chickenpox. That's cute. Okay. So this is the reason, so for susceptible, right? And so this is what makes that, those probabilities, the second set of branches. Let's talk about in terms of a positive or negative test again, because it's hard to talk about accurate and then link that back to positive and negative. So we're better off dealing with that now. And so the two possible outcomes is a positive test or a negative test. Positive test or a negative test. And a positive test or a negative test. We can start with the probabilities of the top branches. 60% is susceptible, so that makes the probability 0.60. 10% is infected, so 0.10. And 30% is recovered, making sure that these all have to add to 1, right? I've split my population into these 3 groups. You have to be in one of these 3. Right? Okay. So now, the next set of probabilities are conditional probabilities, but I'm not going to write them as conditional probabilities, right? And so the test is accurate 95% of the time for susceptible individuals. And then that means if they're susceptible, then it should be negative to be accurate, which means that this probability here is 0.95. Right? Because then it's accurate. You don't have it, could get it, but you should test negative. What does that make this probability? 0.05. Because if you're in the susceptible group, you either test positive or you test negative, and those are your only 2 options, right? And so these probabilities have to add to 1, right? Okay. If you're infected, it's 99% accurate. Accurate meaning a positive result now because you have it. And so now 0.99. And that makes the probability of a negative result 0.01. Okay. How about 65% for recovered individuals? Okay. And so now they're recovered, so they don't have it, so they should be testing negative, which means that this 0.65 is on the negative branch, and that leaves me with 0.35 left over. Okay. I'm going to focus on just this part. Draw a probability tree to reflect the information given above. Technically, this is it, but I do want to see all the probabilities. And by that, I mean, I want to see at the end of each of these branches, you can just multiply through, right? What's the benefit of doing that? Even if you don't need all those branches, then you can add them all up and make sure they add to 1 so you don't miss anything, right? So let's do that. And often I summarize what the combinations are down below, R plus, R minus. I'll show what I'm doing for the first one. The probability of S and positive is 0.60 times 0.05, which is, let me grab my trusty calculator. 0.6 times 0.05 is 0.03. Doing the same thing, multiplying down each of these branches gives me those joint probabilities, right? The and probabilities. And so 0.6 times 0.95 puts me at 0.57, 0.1 times 0.99, 0.099, 0.1 times 0.01, 0.001, 1, 2, 3, good. 0.3 times 0.35, 0.105. You're going to be really hesitant to round, right? Because you need these to add to 1. And in this case, I tend to choose values that give you kind of nice short numbers or relatively short, because now I can make sure that these all add to 1. So 0.03 plus 0.57 plus 0.099 plus 0.001 plus 0.105 plus 0.195 equals 1. Yay! Just a nice little check-in point. Okay. You don't have to make sure they add to 1, but at that point, I mean, what's the harm, right? Show off that you know that they should add to 1, right? But this is a complete tree that I'm looking for. Okay. Now we can talk about the question. If the individual is tested positive, what's the probability that they are actually infected? So again, knowing that they have tested positive, and let me just grab this and put it down. Put her there. So what does this look like? We know that they've tested positive, right? So given that they've tested positive, what's the probability that they are infected? And we write that as what's the probability of I given a positive test. Okay. Rewriting this, right, into kind of simpler math terms, right? That's going to be the probability of infected and a positive test. We already have that probability, right? And so the probability of I and plus, which I've written as just I plus, but it's I and plus, technically, divided by the probability of a positive. Just as before, there were more than one way to get a positive test. In fact, now there's 3 ways that I could have a positive test. So here, there are 3 ways to have a positive test. So the probability of a positive is the probability of susceptible and positive plus, or really what I'm saying is susceptible and positive, or infected and positive, or recovered and positive. Infected and positive plus the probability of recovered and positive. But I have all those probabilities already, so it's not a ton of work. Right, and I will make a note here that this is the same as I plus up above. Right, I cut the and I just multiply them. So now the probability of S plus we found was 0.03. The probability of I plus is 0.099. And the probability of R plus was 0.105. Which is 0.234. So the overall probability of testing positive is 0.234. So now we can get back to the probability. Therefore, the probability of infected given a positive is the probability of infected and positive divided by the probability of a positive. Infected and positive, I'm going to steal it from here. I don't want to scroll around too much. 0.099 divided by the probability of a positive, which we found was 0.234. Usually, I'd kind of walk you through these steps. Part A, what's the probability of infected and positive? Part B, what's the probability of a positive test? And then I would ask you this question, right? And so then you've kind of pulled out all the components that you're going to need. And then I would ask, okay, what's the probability that they are infected given that you have a positive test, right? And then you can just put all those pieces together, right? So I would treat this as 3 parts, but question's the same, the work's the same, right? But usually that's how I would do it. 0.099 divided by 0.234, I get roughly 0.423076921. Roughly. Keeps going. But I don't see any more. So the probability that they're infected, knowing that they've tested positive, is roughly 42.3%. Right? Nice. Okay. They're kind of tricky, but once you kind of figure out how to harness the tree diagram, I find that it's a lot easier, right? You multiply down the branches, and if you need to incorporate more than one branch, then you can add those probabilities together. Okay. Any questions? Okay. Yay, we found the same thing. But they did it way quicker than us. one slide. We did all the work. Okay. I think this is 3.4 because I'm skipping 3.3, I think. It's for small populations and I don't do that. I'll put a little question mark. I know I skipped something, a section in here, but I can't remember which one. I think it's 3.3 and then random variables is 3.4. I don't know. If anyone has the textbook out, you can check. Okay. We're sort of out of the woods for probability, right? So probabilities, we started, right, 3.1 and we talked about, okay, the probability of A and B, the probability of A or B, probability of A given B, right? And all those things. And so now we're on to what we call random variables. Now, random variables depend on the outcome of an event. Now, usually we use a capital letter and usually we use X to denote a random variable. Okay? And so the values that we can get from a random variable, we usually denote with its lowercase, so a lowercase x in this case. And so what we're going to be talking about is the probability that this random variable x equals some specific outcome, lowercase x. Okay. And we're going to talk about discrete random variables, okay, where we only take on integer values. Integers are whole numbers, right? So number of credit hours or the difference in the number of credit hours to this term versus last, that's not really that different. We're going to look at payouts from gambling, right? I know, you're welcome. Where we figure out what the expected value is, the expected value from playing some gambling game, right? Where the particular outcome is, I don't know, I draw a heart or something. And then we just ever so briefly touch on continuous random variables, but then we pick it up and we focus on the normal distribution in the next chapter. And so we are at the very end of chapter 3 here, which feels pretty good. Yeah. But continuous random variables have can take on any real value. So any value between negative infinity and infinity. Negative infinity to infinity. The cost of books or the difference in cost of books, this term versus last, not very creative as an example. So the expectation is one of the main things that we're going to talk about in terms of random variables. Okay. And so the expectation is the average. Okay. So the average outcome of a random variable. So on average, how much money would you expect to make, right? If you're playing this specific game. So we call this the expected value. And often, especially in upper level stats, we talk about the expected value, which is the mean. It is the average. Okay. And so the expected value is the mean. So it's another term for the mean or average, right? this looks different. What did we have before? Before we said that x bar is the sum of our x's over n. There's some similarities here. I've been lazy and I've dropped these indices, right? I equals 1 to k, fine, of x, and then the probability of x equaling that value, okay? But they're actually the same, right? In this scenario here, right? Or maybe before we do that, let's break it down. Mu is the mean, it's the population mean, and so it's the expected value of x. If you played this game an infinite number of times, the expected outcome of this game is this value, okay? And so it's going to be the sum from I equals 1 to k, so over as many possible outcomes as you can have, right, of each individual outcome times its probability, right? And so here, take each possible outcome and multiply by its probability. And then add those up. And then you get the average. Let's do a tiny example just to motivate why these are the same, right? And what we're assuming here. So as an example, what if you have numbers, I give you numbers like 3, 4, 6, and 11. I ask you to find the average. What are you going to do? You add these up, and then instead of dividing by n, right, x bar is going to be 3 plus 4 plus 6 plus 11, whatever that is, divided by 4. What are we technically doing? Technically, you're saying they each have the same probability of happening, 1 in 4. So really what you're doing is you're saying 3 times 1 over 4 plus 4 times 1 over 4 plus 6, times 1 over 4 plus 11 times 1 over 4. So in this case, our x was 3, 4, 6, 11. And we assume that the probability that x equals x is 1 in 4, 1 in 4, 1 in 4, 1 in 4, right? Spread out evenly. Now, it would be very fun to play a game where the probability of winning is just the same as losing and it doesn't really matter. That sounds like a great game that I would want to play, but we know that that's not how gambling works, right? There's going to be some rare outcome that pays off a lot, and then there are more common outcomes that pay less, right? And then there are some outcomes that don't pay anything at all, right? And so what's going to change is this probability is no longer going to be the same for each outcome, right? We're going to adjust it, but really what we're doing is we're taking 3 times its probability of happening, right? It's just we're changing it. 4 times its probability of happening, 6 times its probability of happening, plus 11 times its probability of happening, right? Each of the x's gets multiplied by its probability of happening, add them all up, then you have the expected value. which is a weighted average of the outcomes. Yeah. So we're doing the same thing, just more elaborate, right? And so now, okay. I just had a panicky moment that I didn't start the recording. So let me just, I always worry there. Okay, good. And I'm not on mute, and I'm sharing my screen, so now I can rest easy. Relax. Let's do an example. So the expected value of a discrete random variable looks something like this. So in a game of cards, you're going to win $1 if you draw a heart. Okay? $5 if you draw an ace, including the ace of hearts. Okay? You don't get $6, you just get 5, right? But still pretty good. It's better than 1. $10 if you draw the king of spades, so a very particular card, right? And then nothing for any other card that you draw. Okay? So first we're gonna write the probability model for the winnings, okay? And then we're gonna calculate your expected winnings. Okay, so how are we going to organize this? Let's organize it in the same way that we did in this little itty bitty example, right? I have some overall game, right? X with individual outcomes, right? Or events. And then I'm gonna list the probabilities of each of those beside in the next column. And so here, we're gonna say, okay, I'm gonna let X, or you can call it, oops, hey. We're not interested in the event, but we are interested in what it pays out, X. So X here is going to be the payout, but we need to link it to something. Oops. Let it straighten out. Okay. So we're given some information. If you draw a heart, but then we said, okay, but if you draw the ace of hearts, then you get $5. So it's excluded from this heart mess here. So not ace. You get $1. If you draw an ace, any ace, you get $5. If you draw the king of spades, you get a whopping $10. And then if it's none of those, all other cards, you get 0, womp womp. Okay. So my possible outcomes are 1, 5, 10, and 0. Maybe I'll draw a little divider here. And put some lines on here so I don't go writing it weird. I got squished as I moved down. Okay. I want to find, so first we're going to write the probability model, remembering that a probability model right? First rule of a valid probability distribution, which is a probability model. And so here, sometimes we call this a probability distribution. And we already learned the rules of a valid probability distribution. All the outcomes have to be disjoint, right? So that's our first condition. And that's why if I draw a heart, it can't be an ace because the aces is included here with the aces. Also rules of the game. King of spades is separate from all those, and then all the other cards is, of course, separate. So these are all disjoint outcomes. Okay. And then I list all the possible outcomes, right? In this case, I'm interested in the payout. Okay. And I need the probability of each outcome, right? And the rules for the probabilities are probabilities have to be between 0 and 1. And the total of those probabilities, because I'm looking at all possible outcomes, has to be 1, right? So we know all those rules already, but we haven't really seen them like this yet. Okay, this is where the first part of the chapter comes into play, right? How do I find the probability of drawing a heart that's not an ace? Remembering I have 52 cards in a deck and I have 13 hearts, but I extract the ace. And so I have the probability of a heart that's not an ace is 12 over 52. I'm going to keep it as a fraction. You can convert it to a decimal if you want, but I'm just going to keep it as a fraction. Okay. So then now I'm able to attach a probability of winning $1, right? If I draw an ace, what's the probability of drawing an ace? There are 4 aces in a deck of 52, and so 4 over 52. King of spades, one and only, nice. 1 over 52. And then all the other cards, what can you do? You can take 52 minus 1 minus 4 minus 12, because you know they have to add to 52 over 52, right? And so that's probably how I would do this. Instead of trying to think of all the other cards, right? I'm going to go 52 minus 1 minus 4 minus 12 over 52, which puts me at math. 52 minus 1 minus 4 minus 12 is 35 over 52. So the probability, of course, of drawing any of the other cards is quite high, right? But there's still some probability of drawing one of the other cards. Okay? And so this is the probability distribution. So this is the first part of the probability distribution, or the first part of the question. Then we want to find, so here, this, what can I do here? Right, the probability model for your winnings. I want to wrap that up in orange and just show you where that answer is. There. So I'm going to append to this table, and so that's why I want to kind of keep them separate, but struggling a little bit. Okay. Do I use and calculate your expected winning? So the expected value, going back to our formula, the expected value of X, right? The expected value of playing this game with individual outcomes of X. I take the payout, right, for each individual event, multiply it by its probability, and then I need to add those up. So first thing I'm going to do is I'm going to find X times its probability, right? And then the next step, I'm going to add those up. So here, in the next column, I'm going to have X times P of X equal to X. One times 12 over 52 is 12 over 50. Oops, not 15. 12 over 52. I did like a mashup. 5 times 4 over 52 is 20 over 52. And 10 times 1 over 52 is 10 over 52. And 0 times 35 over 52 is 0. Right? Taking this times this. And you know what? I should probably not be so nonchalant about it. 1 times 12 over 52 is 12 over 52. Clean that up. Now, if I add these up, I'm going to get the sum of X times P of X equal to X. Which is why I kept them as fractions, because I have a common denominator already. And so adding these fractions is relatively safe. And so now I have the sum of X times P of X equal to X is 12 over 52 plus 20 over 52 plus 10 over 52. I'll tack on the plus 0. You can drop it if you want. Making sure you have a common denominator if you're going to add or subtract fractions, right? In this case, they're all over 52, so I'm allowed to do 12 plus 20 plus 10, technically plus 0, is 42 over 52. Which is roughly 0.80769. I need to give myself just one more line. Can I do it? Therefore, the expected payout, right? Because the thing that we're talking about is the payout, and we attach the probabilities of those payouts. And so the expected payout is roughly 81 pennies. Therefore, the expected payout is 81 cents. Nice. On average, right? Is that a possible payout? No. But if you played an infinite number of times, you expect to win 81 pennies on average. Right? It's not really how we, well, it's not really how we should gamble, is it? Playing an infinite number of times. But especially when the expected payout's only 81 pennies. On average for each game, right? But that is how gambling works. Most of the time, we win nothing. More of the time, but than the others, but way less than winning 0. We just win $1, and then we win $5 or we win $10. And so notice, I'll write notice the expected value of X is equal to 81 cents, okay, which is not one of the possible outcomes, but it is the expected payout, which is not not one of the possible outcomes, but it is the expected payout. Yeah. So it is the answer, and you're not going to round it or anything. It is the expected payout if you played an infinite number of times. It's kind of the understanding. Okay. Any questions about that one so far? No? There's variability associated with that payout, right? And so we can talk about the variance of X, and it behaves in a similar way, right? Except now, if we ignore the sum for just a little bit, what are we going to do? We're going to take each outcome, right, or each payout, each individual payout, and subtract the expected payout, right? This is feeling very familiar to when we found the standard deviation, right, or the variance, and we are doing the exact same thing. And so from each of the potential payouts, we subtract the expected payout, and then we square it, right? Makes it positive and blows up any large deviations. And then we multiply it by the same probabilities that we had earlier, right? This is the same probability. This is the same probability we used to find E of X. And then if you want the standard deviation of X, then you would find the variance of X and take the square root. Okay. I'm pretty sure, let me just, okay. Can I cheat and use the slide? Or should we do it by hand? It's on the next slide. Save me some writing. Okay. So here it is. Ta-da! So here's our card game. Now we did up to here, right? We did all this work from here, right, to find E of X. So this we did together. This earlier, right? And we found that the expected value is 81 pennies. Or 0.81. So now what we do, right, is following this here, from each individual payout, we subtract the mean, right? Oh, and they squared it in the same go. Okay. And so we're building out that formula. And so we have 1 minus the expected payout of 81 cents, and then we square it. So a squared deviation of 0.0361. Then we have 5. We subtract the expected payout, square it, and find 17.5561. Do the same thing for each of the remainders. Keeping 0, right? And then we can multiply in our formula. We have the probability on this side, but A times B is the same thing as B times A, right? And so now we take the probability that we had here, right? Notice that this is the same thing that we had here. And we're going to take that probability, and they rewrote it because that's how we see, how we see the entries, right? So it makes more sense to rewrite it like this. And so P of X, 12 over 52 times X minus E of X squared. So 12 over 52 times 0.0361 makes 0.0083, right? Now, if I add these all up, to get the sum of P of X times X minus E of X squared is the variance of X. Adding these all up, because I don't have it, 0.0083 plus 1.3505 plus 1.6242 plus 0.4416. The variance of X is 3.4246. And the standard deviation of X is the square root of 3.4246, which is usually what we're after. Where's my square root? Which is not $1 yet. 1.850567481. So the spread is $1.85. Or $1.85 because it's money. The variance is units squared, and so that's why I avoided dollars squared because it doesn't really make sense, and so that's why we usually go for the standard deviation instead. Okay. So think you can do that on a test? I know you can. What if I was nice and I gave you this table and not the sums, and you had to know what to do with the sums? That feels reasonable, right? Especially because if we go to your formula sheet, oh, not the formula sheet again. I know, right? The expected value and the variance of X is on here. The expected value of X is each of the X's times the probability of that X happening. Add those all up, right? We saw that already. We use this version of the formula. There is another version that I would probably say you can ignore. You can ignore that. We use the first version. If you like the second, okay, fine. If you like the second version better, go for it. What would you do? You'd square each of those X's, 1 squared, 5 squared, 10 squared, 0 squared, multiply by its probability, each individual probability, and then subtract the overall expected value squared, 0.81 squared. And then, of course, the standard deviation is just the square root of the variance. Okay. Good. Maybe I'll bring this in here, copy. And put it maybe here. I know, jumping up a little bit, but. Ignore if you want. If you want to, And also, this is the standard deviation of x. It's the square root of the variance of x. Should put an arrow. Don't ignore the highlighted one because that's the one we talked about. But you can ignore the second one. It's just a derivation of the first. Okay. Any questions about that one? Let's talk linear combinations. As we just saw, these aren't on our formula sheet, right? And so they're more for, I think there's a couple of assignment questions where you have to use the linear combinations formulas, but, and I should have them on the formula sheet, but I'm not gonna test you on it. So here we go. Just good to know. So a linear combination of two random variables, x and y now, is given by ax plus by. So some combination of x and y, right? Where a and b are some fixed numbers, okay, some coefficients. Then the average value or the expected value of this linear combination is going to look like this. So the expected value of ax plus by, well, it behaves kind of the way you want it to. It can wrap around the expected value of each of these things, right? And so we can rewrite this. This is technically true, but it kind of skipped some things, right? This is the same as the expected value of ax plus the expected value of by. But the expected value of 3 is just 3, for example. So then the expected value of a is just a. And so you can rewrite this as e, or a plus e of x and b times e of y, which is what they had here, right? So the e just kind of latches on to the x's and the y's, and it bumps out the coefficients in front. Okay. The expectation or the expected value of a linear combination. Here's an example. So on average, you take 10 minutes for each stats homework problem and 15 minutes for each chemistry homework problem. Yeah, fair enough. This week, you have 5 stats questions and 4 chemistry homework questions. Wouldn't that be so nice? Wow. What is the total time you expect to spend on stats and physics homework for the week? Yeah. So now we have been given the expected time already for a stats homework question. So this is the expected time for stats. In fact, how about for some shorthand, I'm going to let S be statistics, homework problem, and C can be a chemistry homework problem. Okay. Which means that this is really E of S, and this is really E of C. So what we want to find is, okay, if I already know these expectations, we want to find, we have 5 statistics problems and 4 chemistry problems. what's the expected time that I spend on this thing? Now, again, the E just latches on to those variables, those random variables. And so we saw earlier that this is, actually, we'll do the derivation together. I'm allowed to say that this is going to be the expected value of 5 times S plus the expected value of 4 times C. I'm allowed to do that because I told you you're allowed to do that. But then we also know that, okay, the expected value of 5 is just 5. And so I can expand it further and say 5 times the expected value of S plus 4 times the expected value of C. We were told the expected value of S is 10 minutes. And 4 times the expected value of C was 15 minutes. Let's see here. So 50 minutes and 60 minutes, right? Or 110 minutes. Oops. Is how long you would expect to spend on each question. Or sorry, on all these questions. All your homework, can you imagine, done in 110 minutes? Expected to be done in 110 minutes, right? There's variability there that we're avoiding, right? Because we don't have the probabilities associated with each question. Okay. How does the variance work? The variability of a linear combination of ax plus by behaves a little bit differently because when I kind of expand the variance onto ax and by, I'm allowed to do that, but the variance, so here, the variance of ax plus by, I am allowed to write it as the variance of ax plus the variance of by. I'm allowed to just kind of cling it onto each individual term. But what happens when I bump this variance inside onto the x, it squares the a. And that's just something to be aware of. We're not going to spend any time there, really, besides today. Right. But it squares it when I bump it outside. It has to do with the fact that the variance, the units on the variance, right, is squared and they're all kind of connected that way, right? And of course, to find the standard deviation of ax plus by, first find the variance of ax plus by, then take the square root. One thing to note is that we're talking about two independent random variables. Now we're not going to talk about not independent random variables, right? But if they're not independent, then we have to do a little bit more work with that. Obviously, that's not in this course, but it would be in the next course. So it's good to be aware of. But we are assuming that x and y are independent variables, right? What does independent mean? Knowing the outcome of one doesn't affect the probability of the outcome of the other, right? Independent events would be things like I flip a coin and then I roll a die, right? The die doesn't care what happened with the coin, vice versa, right? And so those would be independent random variables. Good. Did I want to do this? This is the one I don't like. No, I don't like this one. Because I just spent a lot of time talking about how you have to pull out the constant and you square it, but then in this case you don't. So that's why I don't like this one. So we're just gonna skip it. It's okay. Like I said, linear combinations, I'm not gonna test you on it, so you're okay. I'm just realizing, fine. But should have cut this example or really changed it for something else. I'll show you why. Why don't I like it? Fine, let's see here. The standard deviation of the time you take for each SATS homework problem is 1.5 minutes and 2 minutes for each chemistry problem. And so we're told that the standard deviation of S, using the same notation, was 1.5, and the standard deviation of C is 2 minutes. What's the standard deviation of the time you expect to spend on stats and chemistry homework for the week if you have 5 stats and 4 chemistry homework problems assigned? Okay, so we want to find, and this is why I don't like it, we want to find the variance of S plus S plus S plus S, 1, 2, 3, 4, 5 plus C plus C plus C plus C, which for random variables is not the same as 5S plus 4C. And that's where I don't like it. Okay. Which does not equal 5S plus 4C with random variables. Which is why I should have cut it. Because now this would become V of S plus V of S plus V of S, blah, 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 5 times V of C, V of C, V of C, V of C, 4 times, which is now 5 times the variance of S plus 4 times the variance of C. Ah, it shouldn't be so sloppy. There. Whereas if I had 5S plus 4C inside, which is probably what we would naturally do, even though we can't with random variables, but that's kind of way beyond the scope of this course. And so then what would I have to do? If I was dealing with this, the variance of 5s plus 4c is 5 squared times the variance of s plus 4 squared times the variance of c, which is going to be different than 5 times the variance of s plus 4 times the variance of c. What's the variance? Square root is the standard deviation, so I can square it to find the variance. So then I have 5 times 1.5 squared plus 4 times 2 squared. Which is some number. My pre-baked notes here, I have 27.25. I'm prepared to just trust that, I think. They probably did some crazy rounding. But then, therefore, the standard deviation of s plus c is the square root of 27.25. .22 minutes. Standard deviation. There. But like I said, I should have cut that one. How about we do a more fun one? A casino game. Now it costs money to play. Uh-oh. Costs $5 to play. That's kind of more reasonable, right? They don't just let you walk in and, hey, can I win some money? Doesn't work that way. So now it costs $5 to play. If you draw, okay, good. First a red card, then you get to draw a second card. Okay, so you have to draw a red card in order to get to draw a second card. If the second card is the ace of hearts, whew, you win $500. Wow, just wow. And it only costs you $5 to play. I mean, come on. If not, you don't win anything, which means you lose your $5. Uh-oh. What's your expected profits or losses if it's negative, right? From playing this game. So the profit is the winnings minus the cost that it costs to play this thing. Okay. What are we going to do here? We have to list all the possible events that could happen, right? And in this case, we're going to kind of simplify it a little bit and say, okay, the event there's really only one way to win, right? First, you have to draw a red card. Then the second card has to be the ace of hearts, right? Otherwise, you don't win anything. So there's really only two possible events that can happen. The one we're most interested in is first a red card, then the ace of hearts. And I'm going to need more room than that. Let me just scooch that over. All the others can be lumped into one category, right? Any other combination of things yields me $0 in winnings. So if we talk about how much I win, right, then I can win 500 or I can win 0. But really what I'm interested in is the profit, right? The winnings minus the cost. And so here you can skip the winnings, but I just want to show it there. So the profit is what we're most interested in. is going to be 495, right? I have to subtract the $5 that it costs to play, right? Or -5 for all the other outcomes. Maybe I'll do it here. 500 minus 5 equals 495, 5, or 0 minus 5. Is -5. So these are the outcomes that I'm really interested in, are these profits. Digging the 495, -5, not so much. But what's the next thing? We need the probability of each of these events, right? And so here we need the probability that x equals x. So the probability that this game yields a red, then an ace of hearts. Uh-oh, how are we going to find that probability? So we need a red card and we need an ace of hearts. Probability of a red card is 26 over 52. Pickle. What's the pickle?
You happen to draw an ace of hearts in the first one.
That's the bummer, right? What happens? You win nothing. You have to draw a red, then you have to draw the ace of hearts, which is one of the reds. So thank you. 25 out of 52 cards possible, right? Because I can't draw the ace of hearts. I have to exclude it. Okay, 25 over 52. Now the ace of hearts is up for play again. And there's only one of them. And I've already drawn one of the red cards, right? And so now my total number of cards is 51, conditional on the first draw, right? So technically we're dealing with a conditional probability. And so I have 1 over 51. I'll highlight the 51 because that's one way that I could sneakily do conditional probabilities. But if I multiply these, I get 25, 25, oh boy. I can do 25 times 1. It's 52 times 51 I want to do. This is going to be 25 over 2652. This is going to be the probability of a red, then ace of hearts. And if I could draw a nice heart, or roughly 0.009, 1, 2, 3, okay, 4, I'll round it to 3. So then the probability of actually getting those $495, it's cost you $5, is 0.00943. Knowing that probability, what's the probability of all the other things happening? 1 minus that, the complement, right? I tell you, okay, the probability that you're going to win is 0.00943, then your brain also knows already the probability of losing, right? And so this is going to be 1 minus 0.00943, which is 0.99057. So now I want to find the expected profit, all right? The expected profit is going to be each profit times its probability, right? In fact, I'm going to call this a lowercase x is going to be x times p of x equal to x. Sorry, sum. There's only two, but I'll throw a sum in there. So next, I can find the probability, or x times the probability that x is equal to x. The profit of 495 times 0.00943, 4.66785. But then I have -5 as my profit times 0.99057. So -5 times 0.99057, which is negative 4.95285. If you add these, plus 4.66785, I get a negative 0.285. That's not good. If you played an infinite number of times, you would expect to lose 29 pennies every time. Or the expected loss, right? Because it's negative, is 29 cents per play. That doesn't sound like a good game to me. I'd want to play it if it had an expected positive profit, but that's not usually how they're set up. Oh, and I guess we need to choose one of these. Well, they're all a loss, so A, B, or C, and I'm gonna go with 30 cents, even though I got to 29 cents, but they like to be pretty frivolous with their rounding, so go for 30 cents or 29 cents. Cool. Any questions about that one? Kind of fun, I think. So by definition, a fair game is a game that costs as much as the expected payout, right? And so the expected profit should be 0 for a fair game. Okay? And so do you think casino games in Vegas cost more or less than their expected payouts? Probably not. Probably not a fair game, but right. So if the games cost less than their expected payouts, then of course the casino would be losing money overall, because the casino itself, the house always wins, right? Because the casino, the house in that scenario, in that saying, plays an infinite number of times. You only go in and you play the odd time, right? And so, yeah, you could, you have highs and lows and whatever, but the house, in theory, plays those infinite number of times, right? And so that's why their expected payout, right, is the overall expectation. Okay. Just some notes to touch on. We already saw that random variables do not work like normal algebraic variables. Okay, so they behave a little bit differently. So x plus x is not the same thing as 2 times x. Okay, we do have a special case. So the expectation, it does behave the same way, but don't let that fool you. Okay, because you would still attach the expectation on each of the variables. And then if you have the expected value of x plus the expected value of x, then you have 2 times the expected value of x. And when you wrap the expectation inside, it just bumps the 2 outside, for example. However, if x and x are independent, right? I flip a coin and then I flip another coin, independent events, then that's going to be the same thing as the variance of x plus the variance of x, which is 2 times the variance of x, which is the example that we saw. But I had just talked about this scenario, and so that's why I didn't like how misleading it was. But the variance of 2x, right, when you bump it inside, you have to square the 2. And so these are 2 different scenarios, but that's okay. This is another one of those I don't like, so we're going to skip it. But it's all on there, so that's why I'm skipping it, because it's the same as what we did before. Any questions about random variables before we just dip in, dip out of continuous distributions, because we're going to look at a lot of we're going to look at the normal distribution next week. So a continuous distribution, now all our outcomes, right? So we earlier for random variables, we were able to list individual events, right? And then that's all we cared about. But now we're on this continuous scale. And so if we look at the distribution of heights of US adults, then we could have this data. Let's pretend we have all this data, right? We have all US adults and we've made a histogram. And of course, there's kind of bins here. But if we had to find the proportion of data, right, that falls in the shaded bins, gives the probability that a randomly sampled US adult is between 180 centimeters, which is here, and 185 centimeters. All right. You think about how do you find the area of a rectangle? Width times the height, some combination of that. Right here, we've broken it up into 2 rectangles, but you can add those areas together and find the total probability. What we want to focus on, though, is that the proportion, I already called it a probability. Proportion is a probability. And the probability for next week, it's going to be really important, is the area under the curve. Okay. In this case, between 180 and 185 centimeters. So, bless you. So if we are able to find this total area, then we have the probability of someone being between 180 and 185 centimeters. Okay. If you've taken calculus, you know that, okay, the area under the curve, that sounds familiar, because then we would have to take derivatives. Oh, we're not going to do that. We should be, but we've got kind of cheater. There's a table that's taken all the derivatives that we could possibly want. And so I'll bring that table. And we're just going to use the table. We're not going to take the derivative, but we sort of are, but we're pretending like we're not. Okay? But the area under the curve gives us the probability, right? Meaning the total area under the entire curve must be 1, right? All possible heights of US adults, if I add up all of them, right, the probability of being any one of those heights should be 1, right? And so we're going to see that. One thing, so what we do is we just kind of smooth this out and we find a mathematical function for this curve. We don't, but technically. And so now we can use kind of the smoothed curve. But one thing, I think the last thing I want to mention and highlight is continuous probabilities are a little bit different than the discrete probabilities, where we found the probability of drawing a red ace, for example, right? We can find those probabilities. However, the probability of a person being exactly 180 centimeters is 0. That's kind of mind-blowing, because what happens if I have the width times the height, but now the width from 180 to 180 is 0, right? 180 minus 180 is 0. So 0 times the height, doesn't matter how tall it is, the probability is still going to be 0. But that doesn't mean they don't exist. It's just the probability of an exact number is always just 0, right? You need to have some width. You could go from 180 to 180.00001, but that's not the same as exactly 180. So I'll leave you with that food for thought. And that is the end of chapter 3. Thank you. If you have any questions, let me know. You've got a slew of things due on Monday, but it is a long weekend, so I hope you enjoy it. And I'll see you on Tuesday.